Okay, hello everybody. So this is a video in which I'm going to solve all of the problems on the practice exam. So, as usual, this practice exam is not really meant to be comprehensive, okay? It's not telling you what is going to be on the exam, but hopefully it gives you an idea of the type of questions that I will ask, how I phrase questions, and I guess the relative difficulty of the material. So hopefully this gives you a pretty good idea. As always, I recommend that you try to solve the practice exam on your own first and then use this video as a way to check your work and to learn from any mistakes that you might have made. Okay, so let's jump right in. Oops, I have some work here already. Gotta get rid of that. Okay, so question one, three-parter. The first part, we're supposed to find all values of theta. Okay, so angles theta such that tan of theta is equal to cotangent of theta. Okay, so here's what we're really asking. Theta should be between, this should say negative pi over 2 and pi over 2. And what we're trying to do is find basically angles for which the ratio of the height of a point on the unit circle to its width should be the same as the ratio from its width to its height. Okay, so in other words, if we have a point xy on the unit circle which theta points at, then we should have that y divided by x should be equal to x divided by y. Okay, the ratio between the height and the x value should be the same as the ratio between the x value and the height. Okay, so this was just how we define these two functions. Okay, so tangent of theta, if we have an angle theta and we put it inside of our unit circle, then tangent of theta was described to be the ratio between the height and the y value and the x value, and cotangent is the opposite of that. Okay, so we want this equation to be true for the point on the unit circle, and we want the angle theta to be between negative pi over 2 and pi over 2. So we're going to limit our frame of reference to the right side of the unit circle. And let's just rearrange this equation a little bit and see if we can get some further information. So what I'm going to do is first I'm going to multiply both sides by x, and I'm also going to multiply both sides by y. And that's going to cause, well, these ones are going to cancel on this one. On the other side, the x's are going to cancel. I'm sorry, the y's are going to cancel. And we'll wind up with the equation that y squared should be equal to x squared. Okay? And if we take square roots, then we get the following. Well, we get that square root y squared should be equal to the square root of x squared. In other words, y should be equal to plus or minus x. Okay, y should be equal to plus or minus x. So I want to look for points which are on the unit circle here such that the absolute value of y is equal to the absolute value of x. Okay, in other words, their kind of magnitude is equal to one another. And if I look on this right half of the unit circle, I can see that, well, there's only 2 points where that's going to happen. It's going to happen in one place when these x and y are square root 2 over 2 and square root 2 over 2. And there's one other place when we're going to get that y is equal to negative x. And that's going to happen down here at the point square root 2 over 2, comma, negative square root 2 over 2. Okay, and we know the values of theta which produce these 2 points. Okay, if we have that, we draw a triangle in here, and what is this really saying? This is saying that the length of one side of the triangle is equal to the length of the other side of the triangle, and that only happens with a 45, 45, 90 triangle. So we can confirm that our answer here should be the two angles theta is equal to pi over 4, or theta is equal to negative pi over 4. So that's how we could solve this problem. Okay, so moving on to the next problem, that we're asked to give a definition of the English word periodic. So you can use a dictionary if you want, but you know, I would just say something along the lines of periodic just kind of means like once in a while. Okay, if I go to the store periodically, then it's something I do on some kind of regular basis, or on some regular basis. Now, we're supposed to explain in words why we call trigonometric functions periodic. Okay, and the way I would answer this question would be to say, well, as theta increases, the values of sine theta, cosine theta, tangent theta, dot dot dot, etc., repeat themselves. Over and over. And maybe I'll even include a little picture. So if we have like a sine graph, what does it look like? It looks something like this, right? And my point here, right, is that, well, if I look at some value theta, like this value theta, and I look at some value theta which is, or some other value which is maybe theta plus 2 pi, then the height of the function is going to repeat itself on every multiple of 2 pi. So that's kind of how I would say, well, I would answer this question, is basically the values of the trigonometric functions repeat themselves on a regular basis, which is exactly what it means for something to happen periodically. Okay. So this last part of this problem, we're supposed to compute cosine of 13 pi over 12. Okay, this is something that's maybe not as likely for me to ask on the actual exam, because it's very easy to just plug this into a calculator, but I want you guys to know how to do it. So I gave it on the practice exam, and here's how we could do it. Well, first of all, if we draw the unit circle, we can try to imagine what 13 pi over 12 looks like. And what is it going to look like? Well, we know that 2 pi is all the way around, and we can rewrite 2 pi as, like, I don't know, 24 pi over 12. And we know that just pi is, you know, going 180 degrees around. But we could rewrite pi by writing it as 12 pi over 12. And then 13 pi over 12 would be pi over 12 more than that. So 13 pi over 12 looks something like this, where in here, this triangle, we could maybe bring it out. This triangle has angle measurement in here. This one is 15 degrees, or pi over 12. And then this one would be 90, and then this one would be, well, let's see, 180 minus 90 is 90, minus 15 would be 75. Okay, so we have a non-special right triangle, which really kind of spells trouble for us in terms of computing this thing, because we want to know essentially what is we're interested in what is this distance of this top leg of this triangle, because that will tell us then what is the x coordinate of this point, x comma y, and that's what we want to know. What is the x coordinate? Okay, so we're in trouble because I don't really know how to solve for the sides of this 15, 75, 90 triangle. So I'm going to need to do something a little bit more clever. Okay, and the clever thing that we can do is we can express 13 pi over 12 as 5 pi over 4 minus pi over 3, I think. No, pi over 6. Okay, so let me explain what's happening here. 13 pi over 12, maybe I'll write these with different colors. Will be pink. So what was it? It was 5 pi over 4 minus pi over 6. So what is that really happening? That means we go 5 pi over 4, that's basically here. Okay, so 45 degrees past 180 degrees. And then we basically subtract 30 degrees from that to get to where we want to be. So if we can express 13 pi over 12 as 5 pi over 4 minus pi over 6, which, let me show you real quick that this does work. We would multiply the denominator and numerator by 3, we'd get 15 pi over 12 minus, well, multiply the numerator and denominator of pi over 6 by 2, that would be 2 pi over 12. And then 15 pi minus 2 pi would get us 13 pi. So this is true. And the benefit of writing this in this way is we know how to find the values of cosine and sine for these two values of an angle. And then we can use one of our sum or difference identities to then figure out where we're going from there. So let me go back to our notes here, and I'll copy them in. I think we're doing a cosine of a difference, so I'm going to copy in. Ooh, this is not going to copy well, is it? Well, maybe I can change it to red, and then I'll copy and paste. So this is the formula that we're gonna use. Okay, so we're gonna rewrite we don't like that paper. We're gonna rewrite our problem as cosine. It was cosine of 13 pi over 12. I'm gonna rewrite that as cosine of 5 pi over 4 minus pi over 6. And then I can rewrite that as, well, in this case the x here is our 5 pi over 4 and the y here is our pi over 6. So I'll rewrite this as cosine of 5 pi over 4 times cosine of pi over 6 plus sine of pi over 4, sorry, 5 pi over 4, times sine of pi over 6. And then to compute these things, well, I just need two unit circles here, and I can see what these values are. Okay, so the first one is 5 pi over 4. And I know that this angle, which is right in here, is going to be 45. And then if I draw the rest of this triangle in here, then I know that this is a 45, 45, 90 triangle. And I know that the point on the unit circle, which is associated to this, is going to have width, which is going to be the point negative square root 2 over 2, comma, negative square root 2 over 2. Okay, so these are basically the values of cosine of 5 pi over 4 and the value of sine of 5 pi over 4. Okay, so then I want to do another one with pi over 6, which looks like a 30-degree angle. So this is a 30, and then I can drop my triangle again, and this is like a 30, 60, 90 triangle, and the point on the unit circle in this case is going to have, well, across from the 30 should be 1/2, so the height of it will be 1/2, and then the width will be that number times the square root of 3, so we get square root 3 over 2. And then these are going to be the values of my cosine pi over 6 and my sine pi over 6. So putting everything together, it looks like square root 2 over 2 times square root 3 over 2 plus, let's see here, sine will be square root 2 over 2, and then the sine of pi over 6 is 1/2. So we get square root 6 plus square root 2 all over 4. And that's our final answer. Okay, so this is a way we can use one of our difference identities to find out how to compute this. Okay. So let's move on then to question 2. So question 2, as usual, I give a bunch of true and false questions. This first one should immediately kind of rustle your jimmies, because we know that secant theta does not actually go with sine theta. Okay, we had the property that secant of theta was equal to 1 over cosine of theta. And we wanted to remember that this is kind of not not friendly for being remembered. So if you can remember that it's maybe the opposite of what you might think, then that's how you could remember that. Okay, so this is true, and also we have that cosecant of theta is equal to 1 over sine theta. Okay, so these two things are not the same, so this is a false. Okay, so the next one looks like some kind of identity here. So cosecant squared theta is minus 1 is equal to cotangent squared of theta. This might be one of the Pythagorean identities. I don't really remember, so I'm going to rearrange it until it looks like something that's familiar to me. This says 1 over cosine squared. I'm sorry, this says 1 over sine squared theta minus 1 is equal to, then the right hand side, cotangent squared theta is cosine squared theta divided by sine squared theta. And what I'm going to do here is just multiply everything by sine squared theta. So multiply this entire thing times sine squared theta. The first thing becomes just a 1. Then we get 1 minus sine squared theta is equal to, on the right hand side, the sine squared thetas cancel and we get cosine squared theta. And if we move this one over to the other side, then we get that this is equivalent to sine squared theta plus cosine squared theta is equal to 1. And I know that this one is true. This is basically the Pythagorean theorem. Okay, so this is the most, I only ever really memorized this one, because all of the other ones, you can do this game of just multiplying things until they look like something more familiar. Okay, so that's that problem. So next up we have some something that which already kind of looks like nonsense. It says that sine inverse of theta is equal to 1. Okay. Well, first of all, this should probably be an x, not a theta. I did that later on too. So why don't we put x? Because remember, sine inverse is going to take an input, which is a y value of a point on the unit circle, and it's going to output a value theta. And then sine is going to take that, and this is basically like saying, well, just the sine function is always equal to 1. Okay, which is definitely not true. We do have the relationship that f of f inverse of x is equal to x. That's a relationship that we had when we talked about inverses. But even then, that wouldn't really apply so well to the sine and sine inverse functions, because as we know, sine inverse can take any value x, which is between -1 and 1, and it will output the value of theta, which is between -π/2 and π/2. So even then, we may wind up with something a little bit more confusing than this. So this is basically nonsense. So sine inverse of x would be equal to x if x is a number between -1 and 1. So false is the answer here. Okay, so next up we've got cosine of 2 theta is periodic with period 4 pi. Okay, so here's what I know. Cosine of theta is 2 pi periodic. And cosine of 2 theta is a horizontal. I'm trying to understand what is the transformation which is being applied here by including this 2 here. Okay, and if we remember back all the way to like section 1.5, we learned about how we do these transformations. And if we multiply by a number which is larger than 1, which 2 is definitely larger than 1, on the inside of our parentheses, that corresponded to a horizontal compression. So if you want to see what this looks like on Desmos, let's see. Here's cosine x, and then we can do another one which will be cosine of 2x. And as we can see, what's happening here is basically the blue function, which is cosine 2x, is wiggling roughly twice as fast, which means that the distance from crest to crest, okay, has also been compressed. Okay, so before the distance from crest to crest was 2 pi, and now that we've compressed this entire thing, it's actually going to have an effect on the period, which is the period is going to be half of what it was before. So we can say then that the period of cosine 2 theta is not double of what it was before, but 2 pi over 2, which is going to be just pi. Okay, so this is checking whether you understand that multiplying by 2 on the inside gives us a horizontal compression and not a horizontal stretch. Okay? So this is false again. And then the last one is just asking us, well, does the graph of secant x have vertical asymptotes or not? Well, you know secant of x is equal to 1 over cosine of x. And this is going to have a vertical asymptote whenever cosine of x, our denominator, is equal to 0. So we can ask ourselves whether that happens or not, and it certainly does. I mean, you can just look at the graph of cosine x. It passes through the x-axis at the points pi over 2 and 3 pi over 2. So that happens for many values of x. Including x equals pi over 2, or 3 pi over 2. So this is a true statement. You can also go back and look at our notes. We drew these graphs of these other trigonometric functions, and the secant x graph looked something like this. Something like this. So we did have these vertical asymptotes. So this is cosine x, and this is secant x. Okay, so that's the true and false section. And next up, we're asked to basically draw a graph of a trigonometric function. Okay, and our original function was like a sine function, and it's been transformed in a couple ways. First of all, we're dividing by 2 on the inside. That's going to give us a horizontal stretch. We've got a minus sign on the inside. That's going to give us a reflection. A reflection about the y-axis. And then we have a 3, which is going to then give us a vertical stretch. Okay, so I'm just going to do these. Okay, so first I'm going to draw sine of x, which, as you know, takes value 1 at pi over 2, 0 at pi, negative 1 at 3 pi over 2, and then 0 again at 2 pi. So here's what sine of x looks like. Oops. So this is sine of x. So let's just apply these transformations one by one. Well, let's do the horizontal stretch first. So now we're going to stretch everything to the right and to the left by twice of what it was. So rather than taking value 0 at pi, we're going to take our first 0 is going to be at 2 pi. So it's going to look something more like this. So this is sine of x over 2. And then if we multiply by 3 out front, well, that's just going to cause everything to move up by 3 units. So we go up now. So rather than taking value 1 at pi, we take value 3 at pi. So this is sine of 3 sine of x over 2. And then to do the last thing, well, what we should do is basically reflect. Okay, so everything that's on the right side is going to get moved over to the left, and everything that's on the left is going to get moved over to the right. So our final thing here is going to look like, running out of colors, is going to look like this. It's going to go down to 3 at pi over negative 3 at pi, and then up to 2 pi, and then so on and so forth. Okay, so like this. So now I can erase the rest of these, I guess, if I wanted to. 3 sine of negative x over 2. Okay, so let me get rid of these guys because I'm going to need to do some other drawings. Okay, so this is what this graph looks like. And then what we're supposed to do is we're supposed to find what is the period of the function, which is given in the first part. Well, the period of sine, remember, is 2 pi. So if I have a horizontal stretch, okay, by a factor of 2, then this is going to double my period. Okay, so the period should be 4 pi instead of 2 pi because we stretched horizontally. And I'm supposed to label this on the graph, so it goes from basically from here to here. This is the period from crest to crest. Should have given a little more space on the graph. Okay, and then we're supposed to find out, well, what is the amplitude of the function? Okay, remember the amplitude of the function is basically the height of the wave from what I sometimes call sea level, I guess. So by that I mean we start on the x-axis and we go up until we hit our wave, and this is our amplitude. Okay, or you could also see it here. The amplitude is this distance of basically how tall is the wave and how deep is the wave. Okay, but we always measure amplitude from the x-axis, so the amplitude in this case, the amplitude of the original function sine is just 1, so if we multiply out front by 3 and have a vertical stretch, then the amplitude is going to be 3. Okay, so that's how we do this question. Alright, so next up, question 4, we're supposed to talk about angles and coterminalness. So, we're supposed to explain in words what it means for two angles theta and alpha to be coterminal. So you could get really mathematical with your definition and say something like theta equals alpha plus 2 pi n for some integer n. Or you could say something like theta and alpha point in the same direction. You know, when I'm asking these types of questions, I'm really just looking for, do you understand the basic idea of what this, word means? Okay, coterminal. It's just to check whether you know generally what this concept is. So I'm not necessarily looking for like a perfect definition. This would be pretty much perfect, but this other one of just saying theta and alpha point in the same direction is also pretty good. Okay, so then we're supposed to figure out whether the angles negative pi over 3 and 5 pi over 3, we're supposed to find out, are they coterminal or not? Well, we can draw our unit circle and think about this. Well, negative pi over 3, that's like negative 60 degrees. So that looks something like this. So this angle here is negative pi over 3. And then if we want to do 5 pi over 3, well, 5 pi over 3, we know 6 pi over 3 would be 2 pi. So we do one less pi over 3 than that. Okay, so in other words, 5 pi over 3, if we converted it to degrees, it'd be something like, well, 5 pi over 3 times 180 over pi. We cancel the 3 and the 180 to get 5, and the pi's to get 5 times, well, 180 divided by 3 would be 60. So 300 degrees. And 300 degrees is 60 less than a full 360. So 5 pi over 3 looks something like this. And both 5 pi over 3 and pi over 3 actually point in the same direction. So it's true, they are coterminal. And if you wanted to use this information to prove it, you could just say, yeah, well, if theta is pi over 3, we get theta plus 2 pi would be negative pi over 3 plus 6 pi over 3, which is equal to 5 pi over 3. So that's a way you could justify your answer analytically, or algebraically. Okay. So that's about that question. Pretty standard stuff, checking whether angles are coterminal or not. All right, and the last part, we're supposed to give the equation of the unit circle. So this is something that I put on the exam because there's a lot of students who seem to not really remember this component of trigonometry, okay, which is to say, well, we have a circle, and I know that the equation of a circle is x minus h squared plus y minus k squared is equal to r squared. And if I'm talking about this circle, then this is a circle with center at h comma k and radius r. So if I want to talk about the unit circle, it's the unit circle that has its center at 0 comma 0, the origin, and radius 1. So the equation of the unit circle would be x squared plus y squared is equal to 1 squared, or just x squared plus y squared is equal to 1. Okay, and then if we want to know whether a given point is on the unit circle, then we just need to check, well, if I plug it into the unit equation of the unit circle, do I get something which is true? So I can try. I'll get 1 over 8 squared plus 7 over 8 squared, and that will be equal to 1 plus 49 over 64, which is equal to 50 over 64, which is not equal to 1. So no. 1/8 comma 7/8 is not on the unit circle. Okay? All right. So that's just checking whether you know what the equation of the unit circle is and how to use it. Okay, question 5. We're supposed to find the value of all 6 trigonometric functions evaluated for the angle theta, and they don't tell us what theta is, but they tell us the values of the coordinates of the point on the unit circle, which corresponds. Okay, so we have 1/2 and root 3 over 2, okay, as our point on the unit circle. So here's a unit circle, and the point which theta points at is the point which is over by 1/2 and up by square root 3 over 2, so it's somewhere up here. Sorry, that should be 1/2 comma square root 3 over 2. And the angle theta is the angle which points at that point. Okay. So this question is then really checking, do you know what the definition of all of the different trigonometric functions are based on the point on the unit circle which theta points at? And the definitions that we had were sine of theta. If theta points at the point x comma y, then sine of theta was just y, and that's square root 3 over 2 in this case. Cosine of theta was equal to the x coordinate, which in this case is 1/2. Tangent of theta was equal to the ratio between the y and the x, which in this case is square root 3 over 2 divided by 1/2, so just square root 3. Then the other ones were just defined from these. Okay, so cosecant theta was equal to 1 divided by y, which in this case is going to be the reciprocal of root 3 over 2, so 2 over root 3, which we can rationalize the denominator. It would be 2 root 3 over 3. And then secant theta, we defined this to be 1 divided by x. In other words, 1 over cosine. So cosecant is 1 divided by sine. Secant is 1 divided by cosine. And it's going to be the reciprocal of 1/2, so just 2. And then cotangent theta is going to be the reciprocal of tangent theta, which is going to be x over y. In our case, we get in our case, we get 1/2 divided by root 3 over 2, which is going to be 1/2 times 2 over root 3, which is going to be equal to 1 over root 3, which is going to be equal to root 3 over 3 after rationalizing the denominator. Okay, and so that's a pretty easy problem as long as we understand where the definition of these trigonometric functions comes from. It comes from the unit circle. We put in the angle theta, and the values of sine and cosine and tangent and cosecant and secant and cotangent are all going to depend on the x and y value of the point on the unit circle towards which theta points. Okay, so that's question number 5. Ooh, my battery's about to die. Better plug in my thing. Okay. So that's question number 5. Excuse me. Okay, question number 6 has to do with the arc cosine function, so an inverse trig function. And of course, on the actual thing, I put theta here instead of x. I should have put x and not theta because the input of this function is not an angle. It should be a value of a point. Okay, and the domain and range of the function arc cosine are as follows. Well, arc cosine takes as input a value x of, well, which is an x coordinate of a point on the unit circle. The domain of a function is the collection of all possible inputs. So in our case, the domain of the arc cosine function is going to be the values of x which can be taken by a point on the unit circle. If I draw my unit circle, it's not hard to see that the minimum possible x value that a point could take on the unit circle is going to be over here at -1, 0, and then all the x values of the points which are in between are going to be somewhere between -1 and 1. So the domain of our function arc cosine of x should be -1 to 1. Okay? To find the range, well, the arc cosine function is going to take a point on the unit circle, and then it's going to give you back the angle theta such that theta points at your x value. And something that we need to remember is that the arc cosine function only has a unique output if we just limit our frame of reference to the top half of the unit circle. So it's going to return the angle theta, which is on the top half of the unit circle, which points at a point on the unit circle, having the x value which was given as an input. So therefore, the range is going to be 0, pi. Okay, so it'll give pi when the input is -1, and it'll give 0 when the input is 1. and that's going to be the range. Okay, so this part was relatively easy to interpret just from the idea of, well, what is an inverse trig function doing? And the range, we have to just remember that the range of a cosine, arc cosine function and arc sine function, we had a very specific set of rules for what the range were going to be for those functions. And that's just really something that's more needs to be memorized than maybe you could find out intuitively. Okay, and now what we're supposed to do is find, for each of these three values of x, we're supposed to find arc cosine if possible, otherwise write undefined. Well, let's start with 1. It says arc cosine of 0. Now, this function should return the value theta such that the x value of the point which gets pointed to on the unit circle has x value 0. And if we consider the top half of our unit circle, well, there's only one point which has x value equal to 0, which is on the unit circle on the top half, and it's at this point right here. It's the point 0, 1. In this case, the x value is 0, and what the arc cosine function is supposed to do is return the angle theta such that theta points at the point 0, 1. And that value theta should be 90 degrees or pi over 2. Okay, the next one, we're supposed to do arc cosine of pi. Well, if we just go back to part A, we said that the domain of our function is from -1 to 1. We can't plug in numbers which are larger than 1, and the number pi is larger than 1, so this is not defined. It's like asking, well, which angle on the unit circle points at a point on the unit circle with x value pi? Well, if we had x value pi, that would be like somewhere way over here. And there are no points on the unit circle which have x value that far out. It's too far away. Okay, so the question doesn't make sense. Okay, finally we're supposed to do arc cosine of -1/2. So I want to find a point on the unit circle now whose x value, and I feel like I'm running out of colors. Pink, maybe. Whose x value is -1/2. So the x value should be -1/2. And then the y value, we don't know. But we can find out what the y value should be by drawing in our triangle. And what this says, the fact that this coordinate, the x coordinate, is -1/2, it says that on this triangle, if we brought it out, the length of this side is 1/2. And we know that the length of the hypotenuse is always 1. And this relationship looks like a 30, 60, 90 triangle, where the 30 is across from the 1/2, the 1 is across from the 90, and the 60 is across from something which should have square root 3 times the length of the side which is across from the 30. So that's square root 3 over 2. So this is the point square root 3 over 2. And we now can recognize that, and I'm running out of colors, this blue angle here is 60 degrees. And I know that all the way from here to here would be 180. So 180 minus 60 is going to give us 120 degrees. Okay? Or, let's see, 2 pi over 3. Yeah. So this is going to be equal to 2 pi over 3. Okay, because 120 times pi over 180 we cancel the 180, we divide both of these by 60, and the first one is 2, and then the bottom one is 3, so we get 2 pi over 3. That's how we convert back to radians. Okay, so that is how we do that one. And the last problem here is asking us to verify or disprove these trigonometric identities. Okay, so we can start with the first one. Okay, it says sine to the power 5 of x times cosine to the power 4 of x is going to be equal to all of this jazz on the right-hand side. Okay, so you could do a couple of things with this problem, and they would all be perfectly acceptable ways of approaching it. The first way would be to maybe look at this thing here and recognize that this looks quadratic in form, so we could factor it, and it would look something like cosine squared x minus cosine to the 4th of x, and then that would be times sine x. We could try to do it something like that, but that doesn't look like it's going to be that fruitful, so I'm going to instead focus on the left-hand side. And in particular, I'm going to use one of the Pythagorean identities. Okay, so I don't think that this is, maybe that would work if you carry on like that, but I think I found a better way, which is to focus on this sine 5th of x and recognize that sine to the 5th of x is nothing but sine squared x times sine squared x times sine x. And then these two I'm going to replace by 1 minus cosine squared x times 1 minus cosine squared x times sine x. And then I'm going to FOIL that out, and I'd get 1 minus 2 cosine squared x plus cosine to the power 4x, all being multiplied by sine x. And then I've also got this term here, which I've kind of left off up until now, this cosine to the power 4x. Multiply that out back, cosine to the power 4x, cosine to the power 4x, cosine to the power 4x. And then I can bring this cosine to the power 4x inside of our parentheses here. And what will it become? Well, it'll become cosine to the power 4x minus 2 times cosine to the power 6x plus cosine to the power 8x times sine x, which is exactly what we have on the right-hand side. So it's true. So we have just verified this trigonometric identity using basically one of our Pythagorean identities, okay? We used the identity that sine squared x plus cosine squared x is equal to 1, and so therefore sine squared x is equal to 1 minus cosine squared x. We replaced two instantiations of sine squared x by their Pythagorean equivalents, and then FOILed, and then brought the cosine to the power 4x into our parentheses there to see that that was true. Okay, and finally, we have part B, which I think is a really cool problem. The reason I think it's cool is it incorporates basically my favorite identities and most people's favorite identities, the double angle or half angle power reducing identities. And here's the trick to seeing this one, although I'm sure there are other ways that you could do this too. But the trick to seeing whether this one is true or not is that we can rewrite the top and bottom. We're going to divide by 2 on top and divide by 2 on bottom. And we rewrite, and it looks something like, so 1 minus cosine of 2x divided by 1 plus cosine of 2x. This almost looks like the result of the power reducing formula. So I'm going to rewrite it in a way that looks more familiar. I divide the top and bottom by 2, and I get 1 minus cosine 2x all over 2 divided by 1 plus cosine of 2x all divided by 2. And now this top thing here is exactly the right-hand side of the power reducing formula for sine squared of x. And this denominator here is exactly the right-hand side of the power reducing identity for cosine squared of x. So in the end, we're trying to check, is tangent of x equal to sine squared of x divided by cosine squared of x? And well, we could rewrite this as sine of x divided by cosine of x, quantity squared. And this inside thing here is nothing but the tangent function. So rewriting, we have basically to ask ourselves, is it true that tangent of x is equal to tangent squared of x? And the answer is no, right? For any value of a number, unless the number is 1 or 0, okay, then if we take it and we square it, then it's going to be a different number. Or you could just divide both sides by tangent and you'd get 1 is equal to tangent of x, which there's all sorts of different x values which will cause this to be false. So this is false for, say, x equals 0, because tangent of 0 is 0. So this would then, 1 would be 1 is equal to tangent of 0, and that would be 1 is equal to 0, which is not true. Okay, so this is how we disprove. Okay, we just need to find one value of x such that the identity isn't true for it. So kind of a clever way of rearranging. There's probably other ways to do this problem as well. There usually are, but this seems like the most simple approach to me. Okay, so hopefully you found this video guide useful. If you found that some of these problems were really challenging for you, then I recommend that you make a note of it and come with some questions about these problems to either office hours or the review session on Wednesday, or talk to the SI about some of these problems as well. So just, you have a lot of resources which you can make use of to study for this exam. So please let me know if there's any way that I can help you guys do that. Okay, that's it for today.